So, welcome back to this Swayam session. So, in the last session we discussed about a recap of the pedagogical terms that we have encountered in this course so far, and we also looked at the definition of transformative education. We didn't get to go through learning theories, which I hope we do today. And we also engaged in a discussion with students, and we will do that in the context of learning theories again, primarily to get a sense of number one, prior experience that students have had in exercise of these learning theories. Number two, seeing whether we can help these students sort of develop a mental habit that is more consistent with the science of learning as we know it as it stands right now. And on a need basis, we will actually start discussion on polymers as well. So, a good way to also summarize one of the outcomes of last time's discussion was the importance of reinforcement in the context of learning. So, positive reinforcement if it is aligned with your learning outcomes, negative reinforcement when it is not, and either ways making sure that there is no perverse incentive or what can be otherwise called a cobra effect. By the way, there are some laws that are actually known in that context. So, when a measure becomes a target, it ceases to be a good measure. For instance, if the student's primary intention and your primary intention becomes students' performance in an exam, and that being the only measure for score in the exam, then it ceases to be a good measure. So, the original intention of having a score is to sort of see whether the student has gotten the learning outcome. But if you put the score over the learning outcome, then that score ceases to be a good measure. So, when a measure becomes a target, it ceases to be a good measure. So, this comes from actually a law in economics called the Goodhart's law, but it is very consistent with human behavior. It is consistent with behavioral economics and education research as well. And in education research, it is actually clearly seen in the form of perverse incentive and the problems associated with it. Okay. So, hence teachers ought to be cautious about perverse incentivizing or teaching to the exam. So, one of the obvious tendencies would be to make sure that these scores which are projected in various scorecards, transcripts and so on and made available for third party evaluation, peer evaluation, etc. Becomes the primary target. But when we do that, there is always a possibility of gaming the exam, and there is always a possibility that we lose sight on the real transformative aspect of education. And this is something that educators should be very wary about, and educators should be deeply concerned about. Okay. So, with that we will continue our discussions on learning theories, and we will look at a set of learning theories that are connected with something that we have seen in the past, and we will use it at least in one materials engineering context. Okay. So, in the past we have looked at something called the Vygotsky's scaffolding technique. And what it basically means is you as a teacher can provide some kind of a framework to the student, and the student fills up the gaps, and hence the full body is sort of made available. So, it basically provides a guided learning approach in some sense, alright. So, that is the Vygotsky's scaffolding, and if you look at the way in which this is conceptualized, this is envisioned, this is visualized, you will find that you are thinking of it as if it is a building. So, you are thinking of knowledge as if it is a building, as if it is a structure, as if it is made up of bricks that are interlinked with one another, interconnected to one another. So, there is a connectionism associated with it, and as a consequence there are what are called as constructivist theories and connectivist theories. Okay. So, this is constructionism. So, it is very similar to building a house, constructivism. So, and it is an ontological approach. And why is it an ontological approach? Because you have a set of key ideas. So just like your concept map, you have various concepts, they are connected to one another, you are constructing these links, you are constructing these arrows, these unidirectional, bidirectional arrows and bubbles and so on, you are constructing a body of knowledge, and so it's an ontological approach, it uses mapping. Certainly your brain has a certain way of mapping these things, there is a neural network way of thinking about this particular problem, and this comes from robust developmental psychology as is known today. Students and human beings in general, mammals in fact in general learn through constructions. So constructivism is that approach, and as a consequence it is meaningful to ask when we write lessons, when we write out lesson plans, when we deliver lectures, what is it that we are constructing, how to construct it, what would be the most efficient way of constructing it. So you could construct a house that is not very efficient over years, or you could construct a house that is efficient, sustainable in a few months. So the design that you take towards it actually matters. So the ontology that you have in place matters. The richness and also the approach matters, okay. So the key here is the construction of knowledge, okay. So this is called the and constructivism naturally yields a constructionist approach. So when you say that the students are set in an environment of constructivism, they basically start constructing. So they become constructionists. They start creating these knowledge maps and they start seeing the connects between various concepts and ideas. They create mental maps, and these mental maps that are discovered by them enable them to actually integrate new knowledge to existing knowledge. For instance, you may know the laws of thermodynamics, but you may not know how it relates to entropy production. But you have a fairly good idea of laws of thermodynamics, and then you have this new knowledge, and how do you integrate this? So how do you accommodate this? So that basically becomes a constructionist approach, and we have seen this in the context of knowledge maps, in the context of concept maps, spider web diagrams and tree diagrams and so on and so on. In fact, in my recent class I use this extensively. I was teaching a course on energy materials, and there for absolutely everything we came up with a schema. Okay, and we said that, okay, how are things connected to one another? Also, can you abstract out and ask, can we construct a design? Can we construct the general features of the tree which needs to be filled up, so that it becomes very efficient for you to sort of see how the different ideas are connected in the context of, let's say, lithium ion battery, in the context of, let's say, sodium ion battery, and so on and so on. Okay, so these are, so it is about information landscaping. Alright. The next one is called Connectivism, and here it is connecting it to the real life environment. So you said that when you were taught some basic computer science, the fact that it is ubiquitous and all around us, and in some sense we live in a programmed world, sort of connected with you, and the concepts in this suddenly seem to actually make sense. They became globally relevant, they became relevant for your life. So your environment, you and what you are learning basically gets integrated, and that is what this concept is, and that concept is connectivism. That is, the social, cultural aspects also get integrated in your thinking. So because the learner is never independent of their culture, their societal environment, their upbringing, whatever, and as a consequence, when they are able to connect something that might be culturally neutral, let's say thermodynamics or statistical mechanics, to their real life experience, to the traffic they see outside, for instance, then it basically becomes real to them. It gets accommodated, it gets assimilated a lot more easily for them, and that actually helps. So this connectivist approach is actually helpful in the constructivist approach, okay, in making sure that you know the mental maps. You are able to create better mental maps, organization. So in some sense it is about having a database through which you can actually navigate. The next one is a very important concept, and that is the concept of constructive alignment, very essential for today's education. Alright, so it is a principle given by this education researcher, Professor John Briggs, is a principle that is helpful in devising learning and teaching related activities and assessments so that they are oriented towards intended learning outcomes. So on one hand, you want this philosophical approach, this transformative learning approach, this constructivist approach, this constructionist students. You need people who sort of are connectivists, who connect to the world around them, and so on and so on. And on the other hand, you also have this time constraint that you were talking about, wherein you have some intended learning outcomes and you have to actually get there. So this is a possible workaround. Although again, from a time management standpoint, how does it actually come together is something that people will still continue researching. In fact, this has been around for about a decade and a half or so, not more than that. So it's a very new concept in education, and it's called constructive alignment. So what does constructive alignment means? It actually means devising learning and teaching related activities. So you design the activities in the classroom environment and orient it towards learning outcomes. So I define my learning outcomes. By the end of this program, the student should be able to solve this, describe this, evaluate this, look at a case study in this particular manner, etc. So I define the learning outcomes, and then I design the activities to achieve those intended learning outcomes, but that alone is not sufficient. You have to give feedback to the student, right? So you have to provide some constructivist feedback en route. You have to keep scaffolding en route, and this approach represents a synthesis of the constructivist and aligned design approach. So the original engineering education paradigm was very aligned design or outcomes oriented. The student should be able to make this robot. The student should be able to program and achieve this. Should be able to write out a prime number generator. Should be able to generate a random number generator. Should be able to do this. So those were the original outcomes. A few decades ago, or even now in many places, it was very outcomes oriented. The student should be able to describe such and such equations. The student should be able to design such and such reactions. The student should be able to design a reactor that is scalable in such and such manner. So those were the problem statements to which there was a response. And that was supposed to be the outcome associated with the course. But now it is not considered to be sufficient, because students learn like this. They will find themselves in new environments. You might teach them something, they may need something else. So unless and until you integrate it, unless and until you use this constructivist approach along with this aligned design approach, unless you mix the two, the student is still not ready for a creative world, where they may have learned something, but they need to sort of build on top of it. And unless they are used to this art of constructing knowledge, they will not be able to do that. So that is why constructivism is very important today, not just in engineering education in general, but very essential, especially to be discussed in engineering education circles, because we have been traditionally very aligned design oriented. And this is something that I actually asked last time, why is that transformative learning is not discussed as often? In fact, that is true. We have been talking about aligned design. Can the student do this? Can the student do that? And even in sciences it has been like this, can the student synthesize these molecules? Can they do this? Can they do that? It was never about how do they actually build knowledge, how do they have roadmaps so that there is sufficient connections, so that as and when there are new problems, new challenges, they are able to take on new challenges. They are able to learn throughout their life. So this approach, as a consequence, is a much healthier approach, and there is a lot of evidence from literature, education research literature, that this is a much more enabling approach for the student. So what the learner does to learn is also essential. So it is not that the teacher teaches, the emphasis is that the learner learns, and that is why what the learner learns, what the learner does to learn becomes very important. This is the central activity in this scheme. Okay, I will continue this. How do you evaluate? The evaluation for this approach, alright, the earlier approach was, as I told you, called the constructive alignment approach. Okay, it was called the constructive alignment approach, wherein you define the learning outcomes, but you also create a mechanism by which they actually reach there, and they have constructed knowledge through their own activities, and you give them feedback so that they construct more and more, the connections become more and more clear to them. Alright, but how do you evaluate this? That becomes a problem, right? So to evaluate this, you can actually use design focused evaluation developed by another education researcher called Calvin Smith. It's an evaluation of the educational process. It's essentially a knowledge survey. Knowledge survey can be thought of as a test. A test is an example of a knowledge survey, but the test is the simplest example of a knowledge survey. However, you can use testing schemes, testing mechanisms along with, let's say, Bloom's taxonomy and so on, in order to come up with a better survey. of what your students have learned. There is a certain, definitely a possibility of that. So you use a knowledge survey or evaluation scheme that focuses on the efficacy of constructive alignment in the course. For instance, I have subject, I have activities, I have intended learning outcomes. You know, how is it that the students have made best use of this? Alright. So the efficacy of it is basically evaluated through this process called the design focus evaluation. It is still something that is undergoing a lot of intense evaluation and research around the world, because it is found to be very relevant not just for university settings but for professional training, and generically helpful for other formative and educational environments too. So this idea that has emerged in the last decade or so is actually very powerful, and it is changing in some sense the landscape of not just higher education but also training and education in general. So how do you actually evaluate the efficacy? So again, that requires design as far as the evaluator is concerned. So let us now do some think, pair, share. So you must have in your classroom settings done some hands-on experience. You must have had some experimental sessions, experimental courses, or even practical hands-on lab courses, maybe programming courses and so on. They are all hands-on courses, experiential courses, and in some cases also project-based learning. Project-based learning, even theory courses can have project-based learning based on whether or not it gives you the freedom to take something of your own, test it out, learn on your own, construct your own stuff, create your own connection, and so on and so on. The question is, are these examples of constructionist approaches? We might not have used this word in the classroom setting, but can you think of them as constructionist approaches? Number one. Number two, what are some techniques we learned that are related to connectivist theories of learning? In class, okay, what are some of the techniques that we have learned in class? This I will respond. You don't have to respond if you don't recall, it's okay. But here, just think about it. So from your own learning experience, what are things that helped you construct your own knowledge? Some of the activities. So it could be activities that you are engaging in now. It could be activities you have engaged in undergrad, which actually helped you with construction of your knowledge base. You understand? You have some knowledge base. You have some knowledge base. You have some. All of you have some knowledge base. Okay. What helped you, or what enables you to construct? What are some of the activities in class and outside of the class that helps with the construction of knowledge? You understand? So please discuss this with one another. Did you understand the question? So it's about construction of your own knowledge base. Okay, what are the approaches you use, for instance? Maybe a teacher is not using it, but you are using for yourself. That's helping you construct your knowledge, okay, your knowledge base. You understand the question? So it could be in class, out of the class, experience, anything that helps you with your own construction. You understand? So what are your initial thoughts?
Critical thinking. Faculty discuss any plot in the classes. So we'll go to the room and sometimes we'll discuss why it is like.
So the plot is given, why is the slope changing, why is this point this way, why. So your discussions with your friends in your classroom, and not in classroom setting, but about things discussed in the class, but your discussions with your friends helped you, especially graphs and plots, those were very helpful. Very good. What about you? What are the initial thoughts?
I usually think like whatever they teach as a theory in class, if I get a physical picture, if they explain with some examples, or I do it as an experiment or an hands-on, I will understand the theory more well.
So hands-on sessions are important for you because you actually appreciate or understand it better.
If they teach something in theory or some concept they are explaining, I will easily forget. I may forget.
Yeah.
It depends upon how interesting it is. I will remember.
Correct. Retention
is like difficult. But if I do something related to that in a hands-on or experimental session, or someone explains me that they have done like this, and because of that only.
So learning experience is important for you.
So if I get an experience with that, I will remember it like many years. Even now, if I recall regarding that subject, I will think of the text.
Yeah. Correct.
Rather than my staff explaining that, if I do it myself, I will remember that and I will go.
Right. So this again reinforces something that is becoming progressively well known among educators. It's not the lecture that matters, it's what the lecture enables that matters. That is why even in the definitions, what the learner does, I emphasize that. So it is not so much what the teacher talks, it is what the learner does. Now the teacher can influence what the learner does. That is basically the facilitation part. So that is where the teacher as the facilitator is becoming important.
My professor who takes a pre-treatment subject. So he usually has like weekly four classes he will have. So 2 will be practical and 2 will be in class. 2 will be in lab.
Oh, so he used to have theory plus lab going happen.
So when he deals with some treatment technique, what he
will show it.
Is like we have separate lab class for the treatment. So that time at the last 10 minutes he will give us one sample. He will tell what are the nutrient conditions we have to keep. So we will keep all samples inside the furnace. He will tell you just do this experiment now. I will explain that in the next class. So he will take theory class in the next class. What treatment we did and what are the properties we can expect from them. In the next class we will go back to the lab. We will take the samples which we already treated and we will analyze for property. If it is like annealing, normalizing or hardening, we will go for hardness testing and microstructure.
Okay. So what he was doing was he was providing sometimes the experiments before the theory before the experiments, but both ways he was not disconnecting or decoupling the theory and the experiment, he was putting it together. Yeah, that requires tremendous sometimes resources. I mean, in this particular case, thank God you had the resources, and you also probably had the right set of courses that enabled this intermingling of things.
That course and that lab in the same semester. Actually that lab will be in the next semester. Course will be in the first semester, next semester only lab. We asked HOD to shift that lab to this semester.
Okay, so that he could co-teach essentially, you know.
So that you won't lose theory classes. We will have lab classes and theory classes at the same time, so we will get more time. Don't have the time constraint.
Right. So otherwise what would happen is you would learn, then there is some decay in learning, and then you would have the next course, and then you have to spend some time sort of picking up. But here, without the decay, it went hand in hand, so it helped with the connectionism part. So the connectionism was there. Your professor used that technique, in fact, wherein he did not want attrition of learning, and he wanted to connect the courses, and he wanted to make it experiential. So that's actually a brilliant strategy. There's no question about it. Yeah, some anecdotes from your learning. You understood the question, right? So did you? What kind of experience, learning experience you might have had, which actually helped you with constructing your knowledge base? So there could be some examples that you give. You could also give lifestyle related things. For instance, a certain learning behavior you have developed, which is constructivist in approach, you know, connectionist in approach, and so on.
Things, I think graphing is the main.
Graphing is very helpful for you, huh?
Because after learning some theory, some formula, and then we take some like technical example, and then plot its behavior.
Yeah.
For example, in the MOOC course itself, we have
the graphing experience was very, very good for you. Yeah, that is true. In fact, even you were saying that, you know, you particularly like to discuss graphs after the classes get over with your friends, in fact. So that is your construction technique. So your friends basically provide the scaffolds, and then the discussions actually provide you with some fillers, and you are constructing your knowledge base that way, right? So this, by the way, might be important for all of us to note, because graphing is coming out. So this is somewhat consistent with what is known in terms of data as well. There are no one set of learning styles, there are multiple learning styles, but most people are visual learners. They would like to see to learn. Some people would like to hear to learn. In fact, that has been the standard assumption. But that is not true. In fact, people mostly are visual learners, and as a consequence, graphing can be a very powerful way of teaching scientific concepts. And in this particular case, the student takes a particular graph with some open problems home, discusses with friends, or thinks about it on her own, or uses props including internet to actually make sense of the points in the data or points in the graph, looks at the change in slope, looks at saturation values, and so on. So he was giving an example of where normalization annealing, for instance, was taught, in a manner wherein there was experimental data that was juxtaposed with real textbook pictures. So it did not seem like something very abstract. It became very concrete because he had numbers, he had units, everything coming together. Even in the MOOC course we looked at the units, if you remember. I said, okay, that's all right, but let us stick to a certain SI unit, right? So it becomes very concrete when you start having graphs plus numbers together. Alright, and graphs can be a very important way for you to sort of have concepts connected with one another. Yes, so what about you, Bodhi?
When I was in school, teachers used to teach like this, chemistry means they used to tell us about some solutions. So solutions they mark by concentrations. So they taught like different equations, modality, normality, all those things. So that time I couldn't visualize all those things. So when we came to lab, means you have to make 1 millimolar solution, the 1 millimolar sulfuric acid or 1 millimolar. Then I did weight, and that make you visualize means all millimolar.
Yes. So that's a very interesting point. So concentration is very nicely defined, isn't it? It's very easy to define also. So for instance, number of moles per liter, number of right, and then similarly we can define normality. Yeah, but a student might find it difficult to visualize this, but now you say, okay, let's just make a 1 molar sodium chloride solution. So what's the gram molecular mass? You may not know, but let's calculate it, because sodium has this mass and chlorine has this mass. So the gram molecular mass of sodium chloride is so much, and then the question is 1 mole of sodium chloride in 1 liter would correspond to how much mass. So you have weighed it and put it, and now you immediately know what this 1 molar solution looks like. It is no longer an abstract idea, it is a very real thing, it is a very real concept for you because you have experientially learnt it, isn't it? Very good. Similarly, I have found that for the first law of thermodynamics, you know, the signs in particular can be challenging to students, but if you can walk them through calorimetry, then it becomes a very relatively straightforward way for them to actually learn about first law of thermodynamics. What are some of the harder concepts that you have studied in your course? It doesn't matter whatever you have, wherever you have come from, whatever your background. And how do you think a connectivist approach or a constructivist approach can help you learn that better? So you understand the question. So discuss with one another what is one thing, and it's okay. It can be something that the rest of the world thinks is simple, but it's somewhat challenging for you, and it's alright, it doesn't matter. But what is this one thing? And all of us have that thing. You know, what is this one thing that you think is particularly challenging, wherein this connectivist approach or constructivist approach, which includes experiential learning, might actually help you overcome the barrier, the learning barrier on. You understand? So please discuss this also with one another. You understand the question? Sort of Achilles heel for you, very difficult concept, wherein we could possibly use the connectivist approach or the constructivist approach for you to overcome that learning barrier in that context. You understand the question? Yeah. So you understand, you will have to suggest a strategy based on the learning theory you have learned, so that you learn this thing that is very hard for you in a better manner. You understand? So you have learned some learning theory, how will you use it to your advantage now? Yeah. You discuss with one another? Okay, please keep.
I could do other part of the mathematics very well. Probably the chapter, I think it is very difficult for me. I used to manage marks, but I don't know why, I mean how. But for understanding, I don't know, I used to understand very little. So I mean, this part even till now, after that, I'm separated from math, but still I find that if there was some more interesting way of teaching
or for learning. So that's what. So you're learning some learning theories now. So the question is, how can you revisit those lessons so that this thing that was hard for you becomes a little bit more accessible, so that there is some self-directed learning. So this is a pedagogical question. Okay, now that you know learning theory, and now that how do you design for yourself, so that you self-direct your learning. So this is difficult for you, alright, but you have learned how the human mind learns, alright, and you have been taught about learning theories, and you have been told about constructivism and about, so the question is, how can you use it to your advantage? You understand? So we will start with you. So one Achilles heel as far as your learning is concerned, one thing that you clearly know you have not learnt or is difficult, and a constructivist way in which you can probably help yourself learn it. Statistical thermodynamics. You are not able to visualize those equations that are used in statistical mechanics or statistical thermodynamics and so on. Yes. Okay. So, what is one way in which you can sort of build a learning design for yourself? How can you design a learning process for yourself in a constructivist manner? So, the one thing we know about learning is you have some prior knowledge, right? You have some prior knowledge. And then you have new knowledge that is coming in, new information, right? And somehow you have to reconcile the two. So, you have to assimilate. That means you should be able to make some connections between this and this. And then you should be able to accommodate. That means your connections should become so good that you are able to use it for solving problems. So, you have prior knowledge, new information coming in, and then as a consequence you have integrated knowledge. Correct? So, what is the knowledge that you have prior to, let us say, statistical mechanics? So, the statistical mechanics becomes the new information and you start making connects, okay, so that you start at least assimilating it, step 1. Eventually, you will start accommodating it so that you can solve problems. That is when you will start having integrated knowledge. So, it is an interesting problem for a given subject. How do you actually do that? So, you will have to look at connected subjects that you understand. For example, you said statistics you understand, but statistical mechanics you don't. So, statistics you understand, mechanics you understand, but statistical mechanics you don't. So, what are the foundational mechanics idea and statistics idea that you need to have in mind so that you start understanding statistical mechanics? So, make a list of concepts that you know, that you are confident about as far as statistics is concerned and as far as mechanics is concerned. In this particular case, even molecular mechanics, it does not matter. And then say, how do they come together in statistical mechanics? What are the new relations that are actually there? So that you start seeing how this gets accommodated into this. So, you have this foundation, you are adding on top of that foundation, you are building a structure, but then you have to iterate so that eventually you are able to assimilate it. You assimilate it, that means you create a fuller concept map, and then you finally are able to accommodate it and then assimilate it. Assimilate it is when you are able to solve problems. Finally, you will have integrated knowledge. Okay, so that can become a problem for you. That can become a semester worth homework for you, isn't it? So, you can come back, for instance, we can have discussions regarding this. What is this basic foundational concept map associated with statistics, associated with mechanics, that we are actually integrating in the context of statistical mechanics or statistical thermodynamics. Alright, very good. Yes, Malik. So, teaching one another, peer instruction can be a very powerful way of improving your ability to accommodate and assimilate new information, because then you are doing. So, the student does. So, the learning is actually essentially connected to action. That is why you see even in participatory learning, it was participatory learning and action. The student is acting. Okay. Visualize, yeah. So, visualizing the reciprocal space is hard because it is a reciprocal space, isn't it?
Something which like theory oriented subjects I can't visualize. So, what I thought is like while watching some science related videos, they will put some 3D visual, something like that. So, no one has seen electrons moving or protons out in glass groups, but they create scientific videos to make us understand. So, what I will do in my mind is like I will picturize whatever the things in the book.
So, you are constructing. You are constructing, he is constructing, and it's perfectly legitimate, because the reciprocal space idea, for instance, is a construction, no question about it. The reciprocal space and the real space being related in a particular manner, so that this is the dual of this. You give the real space, you can define the reciprocal space. You give the reciprocal space, you can actually do the dual on this, you can get back the real space. So this one is a construction, there is no question about it. They are mathematically related in a particular manner, and as a consequence it becomes very relevant for us to actually write it down. It is equivalent to going from, let us say, distance space to wave vector space, right? So and so on and so on. So having these constructions is helpful in mathematical descriptions, and it is okay for you to sort of think of them as constructions, and it is okay for you to sort of design your learning process around it. So you can say that this is a requirement, this is with the basic knowledge I have, and this is the construction that actually allows me to go from here to here. So you actually create a concept map around it. Very good. Okay. But you can ask yourself this question, very clearly, very carefully. You can start with something like e power of I theta, and theta being dimensionless. But at the same time, in real space, the wave is moving through some distance. So that theta has to have some distance factor, but then it has to be normalized, because it has to be multiplied by something that has 1 over distance dimension, so that it becomes theta. So as a requirement for defining wave equations, we had to actually come up with this definition of real space and reciprocal space. The wave moves in real space, but the theta is dimensionless. So you need to have a quantity in real space, and you need to have a quantity in the dual space, also called the reciprocal space. You multiply it so that the theta basically is present. And if you define this well enough, you should, and because theta will be very perfectly defined as a consequence, the reciprocal space is also defined. So there should be a one-on-one map between the real space and the reciprocal space. So you can think of it as a construction that way. You can just think of, so let us say, wave motion as described in high school science as a starting point, and think of the reciprocal space, for instance. That is a perfectly reasonable way of thinking about it. Is anything else?
Because there's like there is a mathematical synthesis, probability and difference. Those days nobody will tell what is the importance of this. We are just simply solving the equation. And then when I came to studying about the magnetism and whatever it is, quantum mechanics, then I realized the importance of that solving the differential equations. So that way the mathematical answer will help.
So as far as you are concerned, knowing the context is an important part of prior knowledge. So if in this prior knowledge box you put context, it becomes easy for you to assimilate new information. Like, it's helpful for you to know that quantum theory is important for solving solids problems, for instance, and quantum mechanical theory relies on differential equations, and differential equations exist in so many categories, families. Then that is new information, and these families are represented in ABC quantum mechanical problems. So that enables you to sort of integrate, assimilate. That's what you are actually saying. Very good. So that's a nice way of learning. So you can revisit your differential equations lessons now and say, okay, what are the classes of ordinary differential equation problems you have looked at, class of partial differential equations you have looked at, which map out to some real problems that you are solving right now. Okay, it could be a problem on atom, on bonding, on whatever, it does not matter, or it could be the strain distribution in a material, it does not matter. So what are these classes and where do they of equations and where do they fit? That way the new information that is coming in is, these are the classes of equations, this is how they look, and this is where they are present, and so you have at least accommodated, and once you go through this many times, you assimilate, you understand. So learning theories as a consequence are helpful in designing your learning process. And finally, you have integrated knowledge. So at this point, we will go to the next question and the next concept, and that is the concept of schema. So we looked at constructivism, connectionism, and here, and think about it, almost all of learning can actually be done this way. If you just understand learning theories, you will be able to plan your learning process, right? So connectionism, and we looked at many maps, for instance, and tree diagrams, spider maps, etc. as an example of this. And then we also looked at constructive alignment. The next thing that we will do is something called schema. And this is an abstract concept. I just want to introduce it especially for those educators who are interested in education research. And also for those of you who have not done education research but would like to do education research, there are lectures by Professor G.K. Suresh Kumar from IIT Madras, and he has talked about research in education. And the lectures are available on NPTEL, and I would highly recommend those lectures for those of you who would like to begin. Certainly action research, but also professional research in education using your own classroom settings and so on. So schema is a concept that comes very often in education, and let us think about it. So it is a pattern of thought or behavior. So it is a behavior. So you transform the learner and then certain behavior starts setting in. And it is the pattern of that behavior. And what does that behavior look like? That behavior categorizes new information and identifies relationship between them. For instance, this is the difference between people coming from different backgrounds. A chemist might actually look at the information and classify it as organic, inorganic, this, that, and so on. A materials engineer might look at it and classify it as, let us say, semiconductors, ceramics, polymers, etc. It might be the same information, but you give it to them, they will actually categorize it differently. And then they link up that information differently. So the schema is what we are actually giving to our students when we train them to think in a particular manner, when they develop a certain thinking behavior, when they sort of accept or they develop a conviction associated with the discipline's tradition. So it is in fact a framework that determines contemporary thinking and also perception of new incoming information. That is what I wanted to emphasize. Like you give the same information to two people, they will think about it differently. No two people are the same. And as I told you, on an average, let us say some people have the chemistry schema, some people have the material schema, some people have the physics schema. You give the same information to them, they will use it in different ways. Okay, one might be an academic engineering researcher, another might be an industrial engineering researcher. You give the same information to both of them, they will come up with two different perceptions on that data. They will come up with two different lines of attack on that data, and that has to do with the schema, the way they take information, classify information, connect the information links, connect the concepts. So that has to do with connectivism. But how those highways of connections exist, those highways of connection that is part of your behavior is really what schema means. Alright, so schema is the pattern of thought or behavior that organizes categories of information. This is also very essential for education researchers because your students might actually have wrong schemas, especially if they have had an Achilles heel, like somebody said that certain concepts in mathematics was hard, certain concepts in metallurgy was hard or whatever, then clearly those schemas are very shaky, they don't even have a schema there. But then the new information you are giving them may need that schema to be present. So then you have to design around it or work with the student to design around that so that their lack of schema or their improper schema is corrected. So there is a transformative experience. So the transformation can also be a corrective experience. So associated with this transformation can be a correction of existing schemas, especially if it is wrong, and integration of a new schema into an old schema so that there is assimilation. You understand? So that there is assimilation. So this is a very key idea in education design research. So here is the question, can we think of the following in terms of schemas? Materials classification. So the moment I give a material, you will classify it. Materials classification. Movie scripts. I know at least one of the people here is interested in movies, so I put that in. Can we think about movie script as a schema? Okay. Then rubrics for evaluation of student response. So the student has responded and I want to categorize his response. I want to immediately put it in boxes. So that's a schema, right? So think about some other schemas that are there, alright. And here is a create level question I have asked. Can we think of using games to develop useful material science and engineering schemata? Schemata are plural of schema. So can I develop games so that chemistry schema are easily taught? So that student, their mental behavior is such that they naturally think that way. material science schema is developed? Interesting question, no? Interesting idea. Can we do it in a game? So that they play a video game and they understand. Okay, if there is a material, this is how I can think about it. This is how I can classify it. This is how I can actually connect this to various concepts. Okay.
And for children, I think there is some learning later.
Yeah, absolutely. Yeah. So why don't you discuss about the possible schema? First of all, are these schemas or schematas? Okay. Are they schemata or schemas? Schemata is the plural of schema. Schemas is also an acceptable plural of schema. So materials classification, movie scripts and rubrics for evaluation of student response. Are they reasonable schemas? Can you think of them as schemas? Can you think about other schemas in your day-to-day life? So please discuss with one another. Okay, so shall we discuss? So do you think each of these are schemas, reasonable examples of schemas? Seems like so, no? Because let us say you see a movie script, you can immediately put it under some category. Classic movies, drama, horror, romance, whatever, one of those. Then materials classification, yes. The moment you have a material, you can classify it as, let us say, polymers, ceramics, composites, whatever. And then if you look at rubrics, a student response comes in, you have to immediately categorize. Question 1, it looks incomplete, complete, in certain manner, it's analytically complete, the formulae are right. So you can actually say, have they used the right assumptions, have they used the right formula? So you can actually come up with a formula and you can fit it into the formula and immediately classify the response, correct? As maybe a high value response, low value response, medium value response or something like that. What are some of the schemata that you can think about? One more example.
Courses also you can take some basic.
Yeah, so the way courses are categorized, for instance, core courses, elective courses, that's a schema. Courses, PG level courses, UG level courses, that's a schema, that's a classification. Science departments, engineering departments, that is a schema, right? So within departments, there are engineering departments, there are God knows how many engineering departments, that's a schema, correct? So they are all schemas. So classification schemes, the moment you hear something, you can, let's say you hear something like atherosclerosis, has to do with blocking of the artery, you immediately connect it to something in medicine, something in biochemistry. So there is a schema in your brain that immediately makes that connections, right? So here is a homework, this is not homework. So think about developing a schemata or schema, one of the two, for polymers. So start just doing information gathering on polymers and see what are the types of polymers out there, what are the variations, can you have more than the traditional kinds of schemas for polymers. So what are the different types of classification mechanisms that are there for polymers? Alright, that is one. Multiple mechanisms may exist, emerging mechanisms may exist. Emerging schema also might exist, number one. The next one is for your Achilles heel. Achilles heel means your weakness. Whatever is your weakness. So you said probability is a weakness. You said something else is a weakness. You said differential equations is a weakness or whatever, whatever be the weakness. Can you now come up with a schema so that you can do this integration of prior knowledge, integration of new information into prior knowledge so that you accommodate, assimilate and you can actually start better appreciating, start solving problems, real problems in that area. You understand? So with that we will come to the very end of this particular session. So what are some of the take homes? Can we just discuss some of the take homes you might have written down in your notes? What are theories of learning? So what are the theories of learning we learned? we looked at Constructivism, Constructionism, Connectivism, and then we also looked at Constructive Alignment as a means of devising teaching learning activities, Constructive Alignment. Then design focused evaluation, increasingly important for not just higher education but for training in various industries, but also in any formative educational environment. You gave me some examples of constructivist, connectivist learnings that you have done. I did not mention this, it is called situated cognition. It is actually very relevant for any kind of education. It basically says learning is doing. Okay, so if you do something, you have learnt it. If you are doing something, you have learnt it. So learning and doing are inseparable, and that is connected to experiential learning. And schema or schemata are the patterns of thoughts and behavior that allows you to classify new information that is coming in. So new information comes in, you have a schema that allows the integration into the prior knowledge, and there is new integrated information that actually comes about. Okay, so this has to do with the tendencies of the mind. The human mind has self-organizing tendencies. We have the ability to make decisions, inferences, etc. And we looked at some common schemata, and you came up with some schemata, and we also discussed in the last class about norm referenced, criteria referenced, and ipsative assessment systems. So for instance, the GATE, the JEE, even when you are using the curve, for instance, for grading, that is an example of norm reference. As I told you, it's very hard to make a case for it. You know, you could make some very interesting logical arguments about why this may not be the best way to actually grade students, but in very large settings, of course, this seems to be reasonable. Criteria referenced, increasingly professional agencies are using criteria referenced evaluations. Ipsative assessment is the student exists here, and through this learning process is he actually going up the scale, Likert scale for example. So that is called ipsative assessment. For instance, the student started at 0 and he goes to 1, 2, 3, etc., etc. So that is basically called the ipsative assessment. So based on the kind of tasks we have at hand, we can use a combination of these or one of these. So you can use norm with criteria, or criteria alone, or ipsative alone, or criteria with ipsative. So it depends upon the task at hand, the learning design that you have in hand, that you actually come up with evaluation mechanisms. And I started out this class in fact by giving this quote called the Goodhart law, named after Goodhart. It's like I have spelled it incorrectly. It is okay. So Goodhart's law, it says when a measure becomes a target and it ceases to be a good measure, and that is essentially a caveat for educators, a caution for educators, because educators should not sort of resort to perverse incentivizing or teaching to the exam, because the objective of education is transforming the learner, enabling her or him to actually live a better life, to be a better thinker, to navigate their life successfully, and it is not limited to the scope of grade in an exam. So with that, we come to the end of this Swayam session. Thank you very much. We will meet once again very soon. Thank you.